record this. Okay, you guys waiting for the person to tell me we're recording. Okay. Okay, so we're just starting the lecture, and then and so what I just said is that we're gonna have a quiz on Wednesday, and then we'll have I'll post an announcement tonight. Definitely 2, 3 trees and maybe some programming review, because I don't want to put the new topic on the next quiz. I decided it's actually maybe one of the more difficult topics, also from grading the quiz. I mean, the finals, I saw some people, I've graded maybe 70% of the finals. I hope to finish tonight. Um, Some people were having a lot of problems on the binary search, maybe because we never had a quiz on or anything. Anyway, this red-black binary search tree can be either, as soon as either get her, they seem not to get it. But let's just start with the 2, 3 tree. So the 2, 3 tree is essentially the motivation for the left-leaning red-black binary search tree. And the remarkable property of 2, 3 trees is that it's perfectly balanced, meaning the number of links we have to go through to go from the root to any leaf. And the leaf nodes are the nodes with no children. The number of links that we go through to go from the root to any leaf node is identical. So you choose your favorite leaf node, and it's going to, the distance from that to the root is the same as any other. So and so that means it's perfectly balanced, and that's what we like. We don't want these long trees. Like we don't want to put a million keys in a tree and just have it just be one super long tree. Otherwise, you might as well just use an array. We want to keep the height as small as possible, and that will reduce the number of comparisons. So we want the comparisons to be more like a multiple of log of n, where n is the number of keys in the tree versus n, right? Because if n is a million, log of n is what, 20, right? So so a million versus 20, it's a lot. Okay, so and also the thing about the 2, 3 tree is that a node can have 2 keys, and if it has 2 keys, we'll see in this example, if it has 2 keys, and there's 3 links coming out of it, and then there are even some, and then as we're building the tree, there'll be times where a node has 4 keys, 3 keys, but with 4 links coming out of it, but those won't remain in the final tree. That's when we have to, what's called splitting the node. So let's just do this. I don't think we did this. Let's just do this review problem, and then we're going to do the same problem only with the red-black binary search trees. But I'll go over the notes first. And I do think it's some of the harder reading, this left-leaning red-black binary search tree. So it's actually the 2, 3 trees. There's no real code for it. It's like a virtual tree. The red-black binary search tree, we take the code for building the binary search tree and just add some steps to it to keep the height as low as possible. Okay, so the first key in this 2, 3 tree, and I'm going to do my best to draw on the screen. That's not working. Okay, so hello. Okay, so I'll see if I can label it. So the first key, that's the only time a key goes into a node all by itself. I'll circle it. It's the only time. It's the first key. It's at the root. It's a root in the leaf node. It's kind of like you're the first in line, the last in line. Okay, so after this, all the other keys will be added to an existing node, an existing leaf node. Okay, so for 2, well, H, well, it's got to be with M, right? H and M. And they're at the root. Now the exciting part starts. And we also keep the keys ascending, and that'll make it easier it prevents errors in the problem, I think. Okay, so the next case, I know that's when I make errors, when I don't make them ascending. Okay, because the next value is C. So there's only one, once again, there's only one leaf node, but see, one thing, let me say before we go on, there are 3 links coming out of this, 1, 2, 3. And this middle link would be, well, the left is everything less than H. The middle link would be everything between H and M. And the right link would point to keys greater than M. But here, like when it's just 1, the first time, M all by itself, keys less than M, keys greater than M. Okay, so now we have this C. Okay, so initially you'd actually have 4 links, less than C, between C and H, between H and M, and greater than M. But, okay, so we are not going to allow a node to have 3 keys in the final state. Okay, so what we're going to do is what's called splitting the node, and then middle key, this is what we did last time, the middle key moves up, and you have H, and you have C, and you have M, and then here. So M has two M's all, so C is all by itself on the left, M is by itself on the right. There's two links coming out. So to the left of this left link is everything less than C. So like this link right here, well, you have to be less than H and greater than C, right? Because to go into this left left leaf node, you have to be less than H, and then yeah, and then if you're going to be to the right of C, you'd be greater than C. The same thing for M. If you're going to be placed to the left of M, you're greater than H and less than M. Okay, but this is splitting the node, and also this is how, when you split the node, this is how you potentially grow the size of the tree, or the height. The height is now 1. The height is the distance. It's the longest, it's the greatest distance from a root over all the leaf nodes. But see, in this case, the distance is the number of links you go through from the root to a leaf node. So in this case, we go through, no matter either C or M, you go through exactly one link. And that's always true of any, that's one of the defining properties of these 2-3 trees. The number of links that we travel to go from the root to any leaf node is the same. It's not going to be 3 for one and 2 for another. Okay, so it's about as perfectly balanced as it can be. Okay, so let us proceed. And the next key is Y. And okay, so Y is greater than H. Y is greater than H. So it's going to be, so we'll join, so so we always join a key with a leaf node. So we'll join Y with M. Okay, so M, yeah, so M is greater than Y. So Y is greater, yeah, so Y is greater than H, so we go to the left, to the right, and we join Y with M, and that's, okay, so now we have 2 keys in here, and that's fine. We're allowed that, so less than M, between M and Y, and then greater than Y. Okay, so then, and then for the C, we'd have just 2, because there's only 1 key in there. Okay, so then, what's after Y? Oh, J. J is one of our favorite keys. J is greater than H. So it's J is going to join that JMY, right? So it's greater than H. So let me draw it down here, because so we have enough room here. So H and C and JMY, right? So we're allowed to have that. Basically, there's 4 links coming out of here. And now, but what happens is, this is why I think it's important to keep it ascending. You're going to move the middle one up, right? So if it's not ascending, it's easy to make a mistake and not move the middle key up. Okay, so when I mean the middle key in terms of its position in the alphabet. So M is in between J and Y, so we're going to move the M up. So we're going to split the note again. And so what do we get here? So we get, but in this case, H joins them. We're not actually increasing the height of the tree. Okay, so we have C down here. Okay, and so then J is in between H and M, and Y is greater than M. Let me see if I can make that a little bit better. Yeah, I'd be a little neurotic about this. Let me try it one more time, okay? Okay, so now we have our 2-3 tree. Our root contains the keys H and M. Once again, the height of the tree is 1, right? You go through 1 link to go to C, J, or Y. Okay, so now what's after J? It's U and Q. Okay, so let's go here. Let me see if I can append this. Okay, so what did I say? U and, I forgot already. U and something or other. U and Q. Okay, so U and Q. So we're gonna look at, okay, so we're gonna add, okay, so there's 7 keys, there's gonna be 7 steps. This is relatively kind of a good problem for a quiz. You know, after a while it gets kind of unwieldy. So we're gonna add U to it. Okay, so U is greater than M. So we go to the right of M and we add it with Y. So H and M, and then C is less than H, J is in between H and M, and then we have U, and then we have Y. Okay, so that's okay, because we have 2 keys, right? We can have 2 keys in a node, and then we add Q. Yeah, so we can add Q. Okay, Q is greater than M, So it goes to the right of M. Okay, so 7. But we're actually gonna have to split the node twice. C, J, Q is greater than M. Right, okay, so that's a J here. Okay, so now the problem is, okay, so that we have 3 keys, right, in one node. Okay, we can't have that. U is in between Q and Y. So we're gonna move the U up. So we have H, no, M, okay, we're gonna move U up to the root. So it's HMU in the root. C is less than H. J is in between H and M. And then, then Q is in between M and U. And then Y is greater than U. Right, because here we actually had 4 links. You can see here that we have 4 links coming out of the root node, okay, and then so we have to split one more time. We cannot have HM and U, because we can't have 3 keys. So we're going to, when we split here, split one more time, and now so in this case we're splitting the root. When you split the root, you increase the height of the tree. So M is the middle one. M is in between H and U. So it's M, H, there's no arrow. M, H, and U. And so C is less than H. J is less than M but greater than H. Q is greater than M but less than U. And then Y is greater than M and greater than Y. And so this is your final tree. In this case, the height is 2, and the distance from the root M to any of those, so the leaf nodes are what, C, J, Q, and Y, and the distance is 2 for anyone. You have to go through 2 links to go from M to Y, M to Q, M to J, or M to C. It's perfectly balanced. So that's the one thing about this tree. Any step, after 7, right, it's perfectly balanced. After step 6, perfectly balanced. And if at some point it's not perfectly balanced, you made an error. That's how I can tell when students make an error. When I see an answer that looks kind of like this, or the shape looks like this, I know that it's clearly wrong because it's not perfectly balanced. So I'll put bad in the 2-3 rule. There can't be a 2-3 tree. I feel like there's something else I wanted to say, but I forgot. Okay, so anyway, I think that's everything though. Yeah. So any question on that, Jose? So there'll be a problem like this on the quiz, or maybe 1 or 2 of them.
Can you hear me?
Yeah.
I was just saying no.
Okay. Yeah, for a brief moment I couldn't hear you. Now I can definitely hear you. Okay, so this is definitely how you create the 2-3 tree. Okay, and so and what we're going to see, so now we're actually going to look at these binary. We're going to go back to binary search trees. And again, you add keys to a binary search tree. You start at the root. Is the key greater than the root or less than the root? If it's less, you go to the left, and if it's greater, you go to the right. And that's how you know where to put a key into a binary search tree. You keep going to the left and to the right. And we're going to do that. But the thing is, we're going to start labeling the links either red or black. And when the first time when we add a key, it's always going to be connected with the red link. And we're going to do is we're going to kind of use this as motivation that we just did right here. So let me just say one thing here is that these links, like with and what we're going to see is that these left-leaning red-black binary search trees, the height is twice log of n. Okay, so let's say like in a 2-3 tree, we have something that looks like this, like B and let's say a Q. And okay, so in the red tree, in the red-black binary search tree, it's a lot of words. Left-leaning red-black. I'm going to put red-black. it would look like this. You'd have Q and the smaller key is going to be the left child of the bigger key, and it's going to be connected with a, and I'm going to use that R to mean red. Okay, so we're not going to have, so all this stuff with like two keys in a node or 3 keys in a node, we're not going to have that. And we'll see soon, but we're not allowed to have 2 consecutive red links. We're not allowed to be able to, we won't have a tree where you can travel through 2 consecutive red links to go from one key to another. Okay, so why don't we actually look at the notes here? And let's see here. Do I have them? Just wrote these today. And then do you see there's a PDF file, and you should see left, this should be online. This should be, I didn't create a module yet, but there should be, I think it's like lecture 2020 maybe, binary search trees or balanced trees.
Yeah, it's balanced trees.
Okay. So hopefully you should, so, and do you see the PDF file that says left leaning red black binary search tree?
Yeah, and rotation.
And yeah, and then but do you see, I just want I messed this up before, that's why I want to ask you. Do you see at the end of the presentation? See, I'm reading at the end of the presentation. Do you see that?
It's loading right now, but I'll bring it up.
Oh, no, but do you see it in the Zoom window when you're watching on Zoom?
Oh, yeah.
Okay, yeah, that's what I want to make sure. Okay. Because sometimes, yeah, I've made mistakes where, oh my God, people don't see the PDF file. Okay, so I'm just going to go over some rules, and I said this is kind of a summary of what's in the Sedgwick book, and I think his is actually the easiest. And I remember it's challenging, and I know the Xi book, there's a Math 140 version of the Xi book which I don't use. I did last semester, and when it came to, I just skipped the red black binary search because it was just incomprehensible to me. I couldn't even follow it. Now we're always going to have the red links when we're when we're done. So after we add a key, you're going to do a bunch of stuff. But when we're done, all the red links are going to be left, are going to be connecting a node to its left child. Now that's not. Now some books will do either left or right. I just think it's easier, and I think it's easier if you just go to the left to understand. Okay. Okay, and that's the way Sedgwick does it. So that's kind of the way I learned it too. In the last lecture, we discussed 2-3 trees. So yeah, so this is what I'm saying. A 2-3 tree is a perfectly balanced tree where all the leaf nodes have the same distance from the root. Yeah, you won't have any interior children with just one. You won't have any interior nodes with just one child node. So leaf node is a node with no child node. So yeah, you won't see anything like this. A perfectly balanced tree, like. See how this just has a left child, but not a right child. You won't see that in a perfectly balanced tree. Okay, and so the height of a 2-3 tree is somewhere between log of 3 and log of 2, where n is the number of, I should say n is the number of keys, actually. So I'll correct that, okay. So a 2-3 tree is a virtual tree. So we don't actually have code for creating this type of tree. I don't think it's impossible if someone wanted to do it. Maybe someone has. Okay. So left-leaning red-black binary search tree. So I do have to correct this. Notice as I'm talking. Is a binary search tree where all links are labeled as red or black. So it's just like what we learned for the quiz, problem 15 on the test. And I gave you a bunch of keys and I said, okay, draw the tree. So it's going to be like that. Only we're going to learn how to keep the tree balanced, so that it's impossible to get these long trees with this method here. So all red links will point to a left child, and so the tree will not contain consecutive red links. So you won't have anything like this, like red, or so I'm saying this would be bad. Or we're not going to allow this situation either. Red or red. So we're going to learn that when you have these you have these consecutive red links, either like this V or this like, line to the left. That's like the equivalent of having 3 keys in a node in a 2-3 tree, and you have to split it. Okay. So we'll learn that in a minute, hopefully. Because I'm gonna go over the cases, then we'll just try some examples here. Okay, so how can we build a left-leaning red-black binary search tree? Okay, so the first key is the root. Okay, so that's the only time so the first key is the root, just like a 2-3 tree. And all the other keys will be added to the tree by connecting to its parent. Oh, this is it's a typo here. This is graphical. Okay, I'll fix that too. Yeah, a lot of little things here that need to be fixed. With a red link. Okay, so when we add it, so except for the first key is the root. All the other keys it's going to be connected to a parent, and the link connecting the new key to its parent will be red. Okay, so let's say we have some key K is connected to its parent with a left-leaning red link, while its parent is connected to the grandparent of K with a black link. Do nothing. Okay, so like here's this. So let's say we have this situation here. We have this tree right here, B, C, D, right? Oh, and here I have this note. A link labeled with R indicates a red link. And now we're going to add A to the tree. You see how we add A as it's the left child of B, and whereas B is connected to C with a black link. So if it doesn't have an R, it's a black link. If it has an R, it's a red link. Okay. So the link connecting B and C is a black link. Okay, and then we just connected A to B as a red link. And so do nothing. We're done. Nothing to do. So that's the easiest case of all. And so this is a this is a left-leaning red-black binary search tree. Very simple one. Okay. Okay, so let's say we connect. Let's say a node is connected. A key is connected as the right child. So we'll have a right-leaning red link, right? And let's say okay, what else? Okay, and let's say the parent does not have a left child connected with a red link, right? Okay, so so what we have to do is we have to rotate left. And I probably should have shown you. I'll show you the code for that in a minute. Okay, so before we do the example, I'll show you the code. Okay, so so here's our tree ABC. We're adding F to the tree. So F is going to be the right child of C, right? F is greater than B. F is greater than C. So F is the right child of C. We always enter as a red link. And now what we're going to do is rotate to the left. Instead of C being the parent of F, F is going to become the parent of C. And that's how we keep all the links. That's how we keep all the red links leaning to the left. And we do this when C itself does not have a left link that's red. So C does not have C, in this case, C does not have a left child that's connected with the red link. Okay, so this is case 2. So there's 4 cases. Okay, so this is the second easiest case. Okay, so F is connected to C. C does not have a left child connected with the red link. We rotate. So basically, we're taking C and F and we're just rotating it to the right. It's kind of like we're taking this. Think of it like C and F. It's like this kind of rigid, kind of looks like there's a bar or some kind of steel bar connecting to it. And we're just rotating this counterclockwise, right? F is going up, C is going down. So it's kind of funny because when you're rotating, you're really not going left or right. You're going clockwise or counterclockwise. So I guess that's an issue with me, maybe not with most people. But we're rotating it. But the link is leaning to the left now, right? See this link here is the link connecting C and F. It's a left-leaning link. C is now a left child of F, instead of F being a right child of C. Okay, so now some exciting steps. Okay, so and I just want to say here, in the 2-3 world, like the trees that we just did, this would be equivalent to whenever you see 2 keys connected with a red link, that's like a node with two keys in the 2-3 world. So like in the 2-3 world, this would be B, A, C, and F. So, okay, so let's proceed here. Okay, so what we can't have a situation, okay, so let's consider this tree right here. Okay, so let's say we start with this. Okay, so C is the left child of D. Okay, so C and D are connected with a red link. Okay, that's fine. Now we're going to connect E to this tree. Okay, so now E becomes the right child of D. Remember, we always always add a new key with a red link. Okay, we're not allowed to have this. See this C, D, and E? This would be like the equivalent in the 2-3 world. Oh, did I leave? I left off my J. I gotta fix it. I guess it doesn't really, but there should have been a J here. I definitely need to fix these notes. Okay, so but in the 2-3 world, this would be G. See, C, D, and G would all be in the same. And then you'd have to split the node. You'd have to connect D to G. But look what we do here is, so this is 2-3. Okay, but what we do here is, okay, so you see we have C, we go up to D, we go down to E, they're all red links. So again, that's like the equivalent of a node with 3 keys in it. So what we do is we flip colors. So the links connecting C and E to D are converted to black links. And now D is connected to G with a red link. That's kind of how we move D up, right? So, because whenever you connect 2 keys with a red link, you're putting them in the same, it's like putting them in the same node in a 2-3 tree, right? So here you'd have, after you split the node, you'd have something like this. And see how D and G are together, and see D and G are connected by a red link. Okay, so any questions on that? So the important thing here is that we flip colors, right? So if you have this upside down V and each link is red, you flip the colors. Okay, that's not too bad. I don't think really any of it's too bad if we practice. It's difficult because it's new. There's lots of rules. It's like, well, why are there so many rules? Okay, case 4, and I have the example on the next page. A key case connected to its parent with a left-leaning red link. And the parent P is also connected to it, like to the grandparent of the new key with the left-leaning red link. So this is the most complicated case of all. Okay, so you have to rotate the link connecting P with its parent to the right. So P actually will become so we're going to exchange the role of P and its parent. And then P is now connected to its right and left child with red links, and then you have to flip colors. So this is the most time-consuming step of all. So here's an example. Okay, so this is our key, this is our tree. So D is the left child of H, it's red. Okay, so now we're going to add A to the tree. Okay, so A is less than J, A is less than H, A is less than D, so we make A the left child of D, and we always add with the red link. But look now, we have these consecutive red links. We're not allowed to have it. Again, that's like a 2-3 tree. Having a node with 3 keys, we have to split it. In the end, we have to split it. So our rule is, okay, so you have to rotate the link connecting D to its parent. We added A, so we go to the parent of A. So what we're going to do is we're going to rotate the link connecting the parent of A and the grandparent of A. Okay, and so we rotate it to the right. So you just think of that link connecting to D and H as like kind of like a solid bar, and you rotate it clockwise. Okay, so now this link here, the link connecting D and H, now is a right-leaning link. And D is the parent of H, instead of H being the parent of D. Also notice when you do these rotations, you're lowering the height of the tree. So this is how we keep the tree balanced with these rotations. And then we have to, okay, but we still have these consecutive links. We have A, D to H. Remember that's our, now we're to case 3. So we actually, we flip colors. The links the links connecting D to its children are no longer red. They're converted to black. And the link connecting D to J is now turned to red. Oh, I guess I can't. Okay, I'll try to fix that later. This doesn't look like a D to me. I'm gonna make some minor editing changes to these slides, okay. Okay, so that's it. So any question on the rules, Jose, before we try a problem?
Is it just a combination of 2 and 3?
Say it again? Number 4 is a
Is case 4 just like a combination of 2 and 3?
case 4 is, yeah, it's kind of like case 2, except we're rotating to the right instead of to the left. Yeah, so case 2, we're rotating. So case 2 is when you have a right leaning link and you rotate it to the left. And I'll tell you, some books would make this optional. They don't care about, we have some books, they implement this algorithm with the red links both to the right and to the left, but we're not doing that. So case 2, we rotate a right leaning link to the left. And in case 4, we're rotating, okay, if I scroll down, in case 4, we're rotating a left leaning link to the right. And then we're combining that with flip colors. Yeah, so we rotate to the right and then we go to case 3. So it's kind of like case 2 and case 3. But yeah, so the first part, yeah, except that we're rotating to the right instead of the left. Anything else?
Oh, not right now.
Okay, I think I've already talked about this. What is the connection between a 2-3 tree and a left-leaning red-black binary search tree? Yeah, so the 2 nodes connected with a red link in a left-leaning red-black binary search tree is equivalent to a node in a 2-3 tree with 2 keys. Yeah, so 3 nodes connected with the red links in a left-leaning red-black binary search tree is equivalent to a node in a 2-3 tree with 3 keys. And then flipping colors is equivalent to splitting a node. And now let me just show you something else here. So we're gonna go back and do this exact same example that we just did with 2-3 trees. Now we're gonna do with red-black binary search trees. And any step, it should be easy to go from the red-black tree to the 2-3 tree and vice versa. Let me just show you something else here. I think I have the code here. I think this is what I want. Okay, so basically this is the code that we add. This is part of the code that you would add to the binary search tree code. Okay, so what happens is, okay, so when we rotate left, okay, so we're just going to change 2 links whenever we do a rotation, either rotating to the left or rotating to the right. So let's say here, okay, so we're rotating to the left, right? So H and X are connected by a red link. Okay, so we can't have that. In this version of the algorithm, we're not allowing that. So we rotate H and X so that link connecting H and X is going to be rotated to the left. So basically X will become the parent of H. So this is basically our code right here, is that H, because the thing is though, is that H is going to become the left child of X. X in this case already has a left child. What's going to happen to node B? So when H becomes the left child of X, node B is going to be sad. Anyway, so but what we do is what we do when we rotate is that so before we rotate, H right is X. Okay, so to actually do the rotation, first you go H right is X left. Okay, so H right is no longer X. So now you actually, at this point, you actually have 2 links pointing to node B. H right, so node B is actually the right child of H, and it's the left child of X. Okay, so then we finish this. We say, well, X left is H. Then we set H to be the left child of X. So we actually end up getting this drawing right here, right? Node B was originally the left child of X. Now it's the right child of H. And H, which used to be the parent of X, is now the left child of X. So that's actually how you rotate left. And notice that node C is still the left child. Node C is still the left. Keep saying node C is still the right child of X, and node A is still the left child of H. Okay, rotating right, and this is for only for flipping colors. So rotating right is, remember, when you have these two consecutive red links. So you rotate the top one to the right. Okay, so here we start with X is the left child of H. And what's going to happen is that H, when we rotate, H will become the left, H will become, it's hard to say these words. X starts as X is the left child of H. And after we rotate, H is the right child of X. So what's going to happen here? X already has a right child. Node B, once again, is now the right child of X. And we're saying we're going to make H the right child of X. So first thing you do is you make node B the left child of H. So after executing this step, node B is the left child of H and the right child of X. And then you go, okay, and now you set X to be the parent of H. You go X right is assigned H. And so you end up with this. So notice that the left child of X doesn't get affected and the right child of H doesn't get affected. So you just change, so whenever you do a rotation, you're changing at most two links. And the rest of the tree is unaffected. So it's pretty wild stuff. But should we actually try a more, that 7 key example that we did for 2-3 trees, do it for red, black, binary search trees? Do you have any questions on this before we continue?
Not right now.
Okay, so let's go back. Was it this? Yeah, was it? I think it's this quiz 16. These are just old quizzes. I'm not sure it's the same. I don't think it's the exact same one, but it's close enough. We'll just do this. Okay, so draw the left leading red, black binary search tree. The results when you insert the keys MGD, XJV are in that order into initially empty tree. So there's 7 keys. Okay, so show every step, and we're going to label it the rotate right, rotate left, flip colors. And I'll do my best to mark it as an R if there's a red link. Okay, so and this can get kind of long, if you have a lot of these, especially that case 4 involves 2 steps. And then when you split, you might have to keep doing more rotations and flipping. Okay, so let's just start here. So 1 is easy. Let me not do it in red. So that's easy. Okay, so 2, well, G is the left child of M. Okay, so there's nothing to do. We're allowed to have left-leaning links. Okay, so now 3 is the first time we're gonna get these consecutive links. See how you have those 2 red links in a row? Remember, that's the equivalent in a 2-3 tree of having 3 keys in a node. So we have to split the nodes. So remember, this is case 4. We have 2 left-leaning links. So our strategy is we're going to rotate G and M. So that link connecting M and G is the left child of M. This is a left-leaning link. The link connecting M to G is left. It leans to the left. We're going to rotate it so it leans to the right. So first we're going to go rotate right. So now we have, and G will now become the parent of M. The left child of G isn't affected at all. And then you're going to flip colors. I'm doing my best here to. And so now you get G, D, and M. So, and that's the shape. That's the exact same. So you see how it's an upside down V. When you have 3 keys, you're always going to get that upside down V, and it's going to go, the left, and it would go in ascending order, right? Because the left child has to be less than the root, and the right child has to be greater than the root. And this is the exact same tree you get if we were doing the 2-3 tree. So 3 keys is always this shape right here, this upside down V. Okay, so now the next key there has to, be a parent of D or a child of D or a child of M. Okay, so we're getting X. It's going to be a right child of M. So we're adding X to the tree. So it's XJVR. And that's going to, so X is greater than G, X is greater than M. So it's going to be a right child of M. And let's put an arrow there. And remember what we said, we can't have right-leaning links. Okay, so this is the easiest case of all. No, the second easy, this is case 2. The easiest case is when you add to the left and you don't have to do anything. Can we add it to the right? You know, when you add to the right, you're gonna have to rotate left. So M does not have any kind of left child, right? It doesn't have a left child. Like if M had a left child that was labeled red, then then you'd flip colors. Okay, but M doesn't have a left leaning red child. Okay, so so we're going to rotate. So we're going to rotate left. This is case 2. And now we're going to make F. We're going to make F the child. We're going to make F the parent of M. Okay, so this step actually does not change the height. Okay, but we're going to keep all these the red links to the left. So you have G is the parent. G is the root. You have D, and now X will become the child of G, and M will become the child of X. And so that's still labeled red. Okay, so M and X, so in the 2-3 world, M and X would be in a node with containing 2 keys. Okay, so then, and what's the next one? So it's J, V, and R, J, V, and R. Okay, so let's do this again. So we're up to 5. We're connecting J to this tree here. J is greater than G. J is less than X, and J is less than M. Okay, so we have G. So it's going to be the left child of M. G, D, X. And we had an M here, and that was labeled red. And then we have a J, I believe. And I'll tell you a common error when I'm grading these things is that students leave off the R's and just, they convert a red link to a black link not incorrectly. So then the rest of the problem's messed up. Okay, so like if I didn't put that R in between the M and the X, if I just forgot about it, I'll stop, right? Because I don't have 2 consecutive red links, but we do, right? So J, M, and X, again, it's like a node in a 2-3 tree with 3 keys in it. We have to split it. So remember the rule? We rotate right, we rotate MX right, and then we flip colors. So there's actually going to be several steps here though, because what's going to happen is that GX is going to become a red link, and we're going to have to rotate that left. Okay, so this is kind of fun in a way if you like puzzles, I think. So you're going to have G. I have a hard time with G. I'm just learning that about myself. Okay, so G and D. Okay, so M will become the parent of X. So G will become the parent of G. M becomes the parent of X. Okay, so the left child of M is still J. Okay, so what do? We flip? No, we rotated right. And then see now once again we still have those consecutive red links. We could actually travel from J to M by only going through red links. We don't want that because that J, M, and X still form it's like a node with 3 keys. We have to split it. So what we're going to do is we're going to flip. Remember we flip colors, and if you don't mind, I'm just going to go down here. So remember, so the links containing J and M and X and M will no longer be red, but the link connecting G and M will be red. So we flip color. So that's kind of the equivalent of pushing M up 1 level. So we get G. Yeah, still let's have that problem with the G's. And D. And then now there's an M here, and this is going to be red, and J and X are no longer red. But what you see how you have there that M and that the M and the G are connected with the red link. That means it's like the G and M would be in the 2-3 tree, they'd be in the same node. Okay, but what's the problem here? Now, some books would say, fine, stop here, but not Sedgwick. He's not satisfied till all the red links are going to the left. So we have to rotate G to the left. Remember, there's 2 links that change. So right now the left child of M is J. Okay, we're going to make the left child of M be G. So what's going to happen to that J? So remember, and the right child of M, the right child of G is M. So what happens is the right child of G, J will become the right child of G, and G will become the left child of M. So we're going to rotate left. So M is now the parent of G. There's a red link here connecting G and M. So they're still in the same, virtually in the same node, but M is now the parent. And then D is the child of G, left child of D. So X is the right child of M, and J is the right child of G, right? Because when you rotate, right, remember, so it's G right is a sign. So when you rotate, it's G right is a sign M left. And then M left is a sign G. So that's how we rotate. So and that's what we have here. M, so G right is J, right? This would be J. So G right is J and M left is G. So if you see here, what do? We added J, so it's 1 and 2. We actually had to do 3 steps. So there's 3 transformations just for adding that J. Okay, but now we have a left-leaning red-black binary search tree. And one thing I can point out here, it's a small tree. If you count the number of black nodes, those are the unlabeled nodes, to go from the root to any leaf node, there's always one unlabeled link, right? So we're not going to count this red link R. And so that's a property of left-leaning red-black binary search trees. The number of black links or the number of unlabeled links to go from the root to any leaf node is identical. So in this case, it's always 1. So what's next? What's after J? J. Okay, so the V and R. Okay, so we're going to add V and we're going to add R. Okay, so let's add V. V is going to be the left. So V will be easy because it's going to be the left child of X. V is greater than M and less than X. So there's nothing to do here. And then it's P, and then this is a D. And then it's D and then J. Okay, and let's make sure there was a D, right? Yes. Okay, so notice about this tree here. So again, the numbers to go from M to any leaf node, you go through 1 unlabeled link, right? We don't count the links labeled R. And also notice there's no 2 consecutive red links. Okay, so all right. So and so this is possibly a valid left-leaning red-black binary search tree. I'll show you a bit before we go. I'll do that, a bad example or like a counterexample that automatically is not a left-leaning red-black binary search tree after we finish. Okay, so then what's the last key? Yeah, so here there's nothing to do. We just added the V, and V is the left child of X. There's no consecutive red links, so we stop. Okay, so then the very last thing that we do is R. And R will become the left child of V. Okay, so I might add, let's add a page here. Okay, so the R is going to be the left child of V. R is greater than M, less than X, less than V. Okay, so we're going to have to do, okay, so this will be so 7, the very last thing, so M. So you can see here, just to be a few keys, there's a lot of rotations involved. So as these trees get higher and higher, they actually just showing each step really can take a long time. Because there's, okay, so this is red, and then we're gonna add in the R, which is it, I keep forgetting it. It's R, right?
Yeah,
Okay, R. R is gonna be red. Okay, so now we're gonna have these two consecutive left-leaning red links. We can't have that. So again, we rotate right, we rotate VX to the right. So we get M, G, just keep my G's are terrible. I need to work on that. I'm gonna cancel all my plans for the weekend and just write G's. Okay, so then, okay, so V will become the parent of X. So V will be the child of M. And now this is X here, and then R here. And now what we're gonna do is, well, this one actually won't be too bad. We're gonna flip colors twice. Right, so we're gonna flip colors. We're gonna flip colors, and you're gonna get an M. And yeah, so the G and the V, yeah, connected with red links. And then the G, D, and J, red links, and then here R and X, no red links. Yeah, so we flip colors, but notice, yeah, so now G and V also, the consecutive red links. So we have to flip colors again. So you get M, G. So now there's no red links at all. And the number of links and the number of unlabeled links, or the number of black links to go from the root to a leaf node is 2. It's all 2 for all of them. D, J, this is a D here. So D and J and R and X. They're all leaf nodes, and you go through exactly 2 unlabeled links to go from M to a leaf node. And that's a defining property of these red-black binary search trees. So any questions, Jose, before I just want to show you one example?
no.
Okay, so suppose we had a tree like this. It's something like this in the book. So he has a tree like this. So let's see, go from here. I'm not even putting the keys in. Okay, so you go through 2 black links and then. And you guys say, is this a valid red-black binary search tree? Well, you know that it's not, because look here, 1, I go through 1 black link, 2 black links, 3 black links. Here, let me just put one more in here, okay? Okay, but see, there's 3 unlabeled links to go from, oh no, let me do this again. Okay, this would be unlabeled, labeled, okay, so this would be a labeled link. Unlabeled link. So there'd be 2, and then let's just make this, here, I'll take this back then, okay. Okay, so to go from, let's say, to go from, let's say, like from here to this node here, you go through 1 black link, right? But to go from the leaf node to this one here, you go through 2 black links. It can't be the result of a left-leaning red-black binary search tree algorithm, right? So the number of unlabeled links always has to be the same. So, and we'll do some more of these multiple choice type problems next time. So, and also doing one more example of a red-black binary search tree. So do you have any questions right now? So we're going to do more of this next time. And then, and I'll post your announcement about the quiz. Definitely 2-3 trees, and there'll be one other kind of programming topic that I'll post tonight online. But do you have any questions right now?
No, thanks.
Okay, so let me just unshare here. I'm going to stop the recording.